right, let's get started. Good afternoon. We're going to continue discussing security at a somewhat high level today. Hopefully you guys have read this paper about Google's security architecture and overall sort of design. So today we're going to start talking about security from a somewhat higher level. What I mean by this is that security sort of you can worry about it at many levels of abstraction. At the end of last lecture, we were diving into some details of x86 instructions and buffer overflow details. And it's important to get those details right. But those are really sort of fixing specific bugs. It's very attack specific. So you worry about buffer overflows. You go fix specific bugs in your code to prevent that from happening. But a different sort of way of thinking about security is much higher level. And instead of trying to fix specific bugs or very specific attacks, it's good to also think about broadly what is important in your system and how do you prevent attacks in general from damaging what you care about. So in this lecture, we're going to look at, by security architecture, I mean things that really are going to defend your entire system against maybe a class or several classes of attacks, instead of worrying about very specific things. And ideally, we'd even like to be able to design a security architecture that might help you even deal with things that you don't know about yet. So some unknown attack that comes out, wouldn't it be cool if we could build a system that was, to some extent, resilient to attacks that we haven't worried about yet? Not always going to work, but it's good to try to think about this stuff. And in some ways, the main way we're going to use to deal with attacks we don't really know about in detail is to try to contain damage. So the way to really think about unknown attacks is to worry about what if every part of your system gets attacked and broken into, and then structure your overall system so that it's not too bad. Even if an unknown attack happens on a component which you thought were perfectly secure, well, your architecture might limit the damage so the bad guy doesn't get to cause too much harm to the overall system. So that's what the sort of context for this paper is. That's what we're trying to extract out of it, even though it's a fairly extensive description of what Google does in various ways. That's what we'll try to focus on. Hopefully. Make sense? Questions about this stuff? Hopefully, so far so good. I should remind you guys, there's this anonymous question asking link on the web page. If you don't want to raise your hand, you can type questions in there, and Noah will anonymously relay them to us. All right, so let's talk about this particular Google case study that we assigned for you guys to read. So in order to figure out what their security architecture is, we've got to figure out what it is that we're trying to protect. What do these guys care about? What do they want to guard in their architecture? Yeah?
Six different layers of their whole pipeline, starting with hardware and
Well, so 6 layers, you're describing sort of, where they worry about attacks. But like, what matters to them? Like, what would be damaging if it went wrong? Like hardware would, like whatever, they might, some hardware might get thrown out the window, but that's, yeah, one second, yeah.
They don't want people who they don't want to control their architecture.
Control architecture, okay, so, so what would go wrong if someone controlled the architecture? I don't know what that quite means, but, yeah. Yeah, okay, so that seems like a big one. End user data. So if they lost user data, that would be kind of unfortunate. Happened yesterday. I was like actually answering a bunch of questions from all of you, and I Googled around. There's an article from Google Photos losing user data yesterday. Happened back in November. They only publicize it now. So it happens, but anyway, they have an architecture that tries to prevent it. Yeah, end user data. I think you see actually a lot of the architecture is geared towards encrypting data, protecting who has access to it, controls of what employees do, et cetera. So I think that's one of the big drivers for them is keeping integrity and confidentiality of user data. Are there other things they worry about attackers sort of violating here? Yeah? Yeah, that's a good one. Actually, somewhat separate from user data. Right? Like maybe your data is perfectly safe in some data center, but just can't get to it. That's, half the problem is right there, availability. So that's also a big problem for them. They'd like for their services to keep working and be reliable, yeah. Other things? I think it probably covers. It seems pretty broad. I imagine maybe one thing you could imagine sort of fitting in here tangentially is maybe some sort of accountability. that if something does go wrong, they want to pin down what happened and why and fix it again. Although it's really secondary too. Like if they got the first two goals right, they wouldn't really need accountability. But very much in the spirit of containing damage, that seems important as well. Make sense? Other questions? Comments? All right. So how do we go about this? Well, so we figure out what we want to protect. And it's also important to figure out how much you want to be paranoid about this stuff. So what kinds of threats are we going to try to worry about? So what do these guys worry about in the paper? It's pretty extensive, actually. Yeah. Impressive how much they are paranoid. I guess I'll start off the list. They certainly worry about bugs in software. I think they don't really trust their software to be completely bug-free. What else do they worry about? Yeah? Access control? So access control seems like a good sort of, mechanism for something, but what's the attack? Sure, yeah, unauthorized access seems like a good one. But like, what would go wrong? Like, why would someone break in? So I guess maybe one thing is, password theft or something. So if someone steals the password of a user, that would be unfortunate. If someone steals the password of an employee, also bad. So I guess by that argument, insider attacks also they worry about a bit. So employees that either because they are themselves malicious or because their password was stolen or because their computer was taken over by malware, it might be that employees appear to be doing something undesirable in the overall system. So a common sort of good thing to keep in mind is that the reason why many systems worry about insider attacks is not necessarily because they think their employees are out to get them, but it's sort of a good mental model to think about where your employee's credentials or laptop or something else might get stolen, and then that employee will appear to be malicious. Although I think in this case they're also worried about accidentally hiring, the large company, so they might hire someone that is indeed trying to damage some, thing they care about. Make sense? Yeah. Yeah, actually, that is a surprising thing. These guys are really hardcore. They worry that the hardware is out to get them. So might be some bug in hardware or some backdoor in there, or yeah, indeed, misprogrammed. Yeah, actually, network's a big one, and in practice, probably certainly higher up on this list than it appears. Yeah, like the network could be compromised, controlled by the adversary, the internet for sure. But even internal networks, they worry about this as well. Internal in a data center, links between their data centers, they worry about someone snooping on that. Absolutely. Other things that you guys picked up? Yeah. Yeah, so physical attacks on what? Yeah, like someone, break in, yeah. So they worry the data center better be, closed, locked, all this stuff in a cage. Indeed. That's a pretty long list. It's indeed, I think one nice thing about this paper is how holistic it is. Like, it really includes a lot of stuff. Like, about the only thing it leaves out is the end user device, like Android or the Chrome browser in your machine. That's not really covered. They have a sophisticated story there too, but everything that happens sort of in the data center onwards, this paper covers. Like, to the extent that, who knows, maybe there are some details left out, but it is an impressive and interesting read. All right. Yeah. That's a good question, yeah. So why is Google writing this paper? Well, why would they? I guess we were talking about, okay, last time, defense in depth. It seems like, sorry, defense in depth seems like a separately interesting story. But what I meant to say was, last time we were arguing, well, security by obscurity maybe is like a bad plan because then more people will audit your code, et cetera. But this seems like there's nothing really here that other people will audit and say, oh, but you like your hardware plan is wrong. No one is going to look at this and sort of inform them of a weakness in their plan. It seems too high level for that. So what are they getting out of this plan? It's not like someone's reviewing it. Yeah. Yeah, so one thing you certainly, a bunch of you guys commented in your questions is like, the last section is like fluff. So it's all interesting, and then basically a restatement saying, well, if you're a customer of Google Cloud, you'll get all this great stuff. So I think one is marketing for Google Cloud, seems to be that. Probably another aspect is they're trying to convince the public or potential customers that they actually get the stuff right. So actually, like the degree of sophistication they go to keep customer data secure is quite impressive, and maybe it means you should use Gmail if you really care about security, or plausible at least. Yeah. Any other thoughts? yeah, so I think it's sort of some degree of marketing, some degree of sort of trust and building and getting a security community to appreciate them as a leader in this space. So let's try to understand, I guess, what their platform looks like, or environment, or what have you. They never really draw this picture out in the paper, so it's helpful to try to understand what is going on. There's so many moving pieces. So as far as I understand, infer from their paper, their worldview is basically divided into a bunch of data centers. So here's one data center, and they have many of these things out there connected by links, wide area. And what they're talking about is what goes on inside of one of these data centers. And what's going on is that they have a whole bunch of servers, server machines in here. All of them are probably running some kind of a virtual machine monitor. In their case, I think it's all Linux KVM to the first approximation. So a bunch of servers, all running Linux KVM. On top of this, they have a whole bunch of virtual machines running. So these virtual machines are running on top of KVM. And inside of these boxes are all their applications and cloud customers and services and what have you. So you might have some, service A over here, another service B over here. They talk about services spanning machines. So you might end up with service A running on this server as well. And then they have some other things that, I don't know if they quite the services, but what I'm talking about is this Google front-end piece that is kind of special in their architecture. But we'll talk about that in a second. So that's sort of the breakup. It's data centers with lots of servers, of course, connected through some Ethernet network here. And the way that something interesting happens is almost always an HTTP request comes in. And HTTP requests go to these special Google front-end servers. These guys handle every HTTP incoming connections into Google. And their job is to turn HTTP into some more structured and security-friendly format and good for other things. This is the RPC layer that they talk about in the paper. So RPC is the way all these services, all these boxes are going to communicate through a standard RPC protocol, which means that you send a message to another machine saying, I want to run operation X on these arguments, and you get a response back saying, done, or here's an error, here's the result. So everything has a standard RPC library, and this Google front end might take an HTTP request, transform it into an RPC call over here to service A. And then service A might say, well, I want to call this other service as well. So there will be another RPC call here. And then eventually all these RPC calls will rewind, and GFE will get the response to HTTP request, send it back to the user. So I think that's the high-level picture that these guys have in their mind of how all the software is going to work. GFE converts the external world to their nice internal RPC plan, and then all the services just talk to each other through these RPC calls. And they're all running as virtual machines. Make sense? And potentially you can imagine this crossing data centers as well, so it doesn't have to stay within a single data center. Questions about that? Hopefully, yeah?
If you're worried about attacks over the network, why wouldn't they use HTTPS?
Oh, so sorry, yeah, here I'm sort of taking HTTPS for granted. You're absolutely right. Well, they have to support HTTP for, if you want to talk to it, they also support HTTPS. They make a big deal that GFE is careful about certificates and all that stuff. And actually all this RPC internally is also encrypted. So you're absolutely right. I just didn't want to complicate the picture because we're going to have a whole 2 lectures on HTTPS. Yeah, but indeed, you're right. Other questions about this high-level picture? OK, so let's try to understand how we're going to think about security at this high level without worrying about bugs. So I'm going to sort of give you guys some high-level way of thinking about security, and it all has to start from isolation. So isolation is basically step 1 in building any secured system. You have to be able to take components and keep them apart from each other. You've got to basically build those boxes that I drew around the various services in that diagram. So super important that you be able to place, A, B, and C all in different boxes here. And the way to think of it is that we're going to have some host. We'll talk about these hosts in just a second. But something is going to keep A, B, and C apart from each other. And what it means to isolate is that A, B, and C are running, and they just cannot poke each other in any way. It's like A cannot touch and mess with B, B cannot mess with C, and so on. If you don't have isolation, there's no hope for any kind of security, because everyone can mess with everyone else. So the first part is going to be to build these boxes in a good way. That's roughly the first half of this whole class is going to be about boxes. And then you need to have some kind of a sharing plan, which we'll talk about as well. So what am I talking about? What are these boxes? So what kinds of boxes do you guys see in this paper? What are they isolating from each other? Yeah, so services are what goes in the box for sure. How are they keeping the services from each other? Well, it's not, the credential is not going to prevent A from just like poking at B's memory. That's what I'm talking about, yeah. Yeah, so virtual machines is certainly one part of this story. So this picture actually like shows up at many levels of abstraction. So all the credentials and sort of interactions are going to help us worry about sharing when they want to interact in some limited way. We're going to need all this machinery. But step one, keep them apart. And sort of virtual machines is absolutely a good part of the story. So who's the host? Who is keeping the VMs apart from each other? Well, it's the virtual machine monitor, right? So like Linux KVM in the kernel is carefully written to make sure that this happens. Are there other stories for isolation that these guys have in the paper? Yeah?
They each have identities.
So user identities are sort of well and good, but they're not keeping like pieces of code from each other. User identities help you decide maybe when to keep it away from each other. What kinds of hosts are keeping boxes separate? Where else do you see isolation in sort of software? Yeah?
Some services are their own host to protect against hypervisor exploits.
Like a whole machine, right? Like, yeah, absolutely. So like separate servers. And absolutely. And the host is basically physics, if you will. So physics says, well, it's just like a different thing. You can't poke it. There's like holes in all these things, right? Like none of these boxes are going to be perfect, but it's good to have sort of at least to first approximation, it's a good box, and then we can talk about, well, there's ifs, buts, and what have you. But absolutely. So I think what's going on in Google, the paper mentions a little bit about using separate servers. I think the service they use for managing keys is probably just like a separate server in a rack. Maybe it's a separate rack, who knows, to make sure that if the virtual machine monitor in Linux KVM turns out to be buggy, well, that's now these boxes are not real boxes. This boundary is fake, but at least the boundary around this box implemented by separate servers, that's good. So that's absolutely, yeah. So there's varying degrees of security for these boxes, as you can imagine. Other situations that these guys show up with isolation, or that you can imagine doing it otherwise, yeah. Yeah, I guess, yeah, if you're worried about, yeah, so data centers, absolutely. So that's just, yeah, another level of paranoia, but absolutely, yeah, oh, indeed. Probably, yeah, indeed. On the smaller scale, you could actually think about other things being these isolation boundaries. So for example, languages. So like in JavaScript, you can run a piece of code in JavaScript and just don't give it access to any of your shared variables. And then it'll be sort of an isolation. So you could use a JavaScript language or JavaScript interpreter as the host for isolating different JavaScript modules from each other. Same thing for some other languages as well. Java, some languages don't isolate well. Like it's a nice language, but there's no way to box it up. Code can always get out. JavaScript, I think, is pretty nice. You can actually box it up. So you can see this idea sort of showing up in many forums in real systems. Questions about this stuff? Make sense, sort of? OK, so once you have stuff in boxes, all these different services isolated from each other, you're going to want to try to allow them to still communicate with each other somehow. So it's almost never the case that you want to completely split stuff up in boxes. So it's important to box stuff because now you can, for example, have a highly sensitive service and it doesn't have to worry about what's bad in other boxes. Or from another point of view, you can say, well, we'll stick some really untrusted code like one of these Google Cloud customers. Who knows what the hell they're running. But they can run whatever they want in this VM box, and that's OK. They can't get out. Powerful idea. But then if you're building a large system like Gmail or what have you, it's going to be composed of multiple boxes talking to each other. And the model that I want to propose to you guys for how to think about all these different services interacting and sort of having some degree of sharing is what's often called in the security community the reference monitor model, or the guard model. And what I mean by this is what we're going to have is our nice box from before. And inside the box is something you want to keep protected. So some kind of a, let's say, a resource. Something is in a box. And we get a request. Comes in, wants to do something to our resource. This might be a file, might be all my Gmail data, might be some, I don't know, device, who knows. How do we protect it? Well, this is not literally like a code library that I want to propose to you guys, but sort of a way to crystallize your thinking about this problem. Think of this isolated box having some sort of a guard that's sitting in front of the resource. So its job is to take the request and figure out whether it should actually happen on the resource or not. And there's really sort of two other things that the guard needs to know. One is there's a policy. The guard is going to look at the policy and say, well, policy says you can do it versus you cannot do it. In order to help answer this question, we need to actually have the guard figure out who is trying to issue this request. Depending on who is trying to do it, it might or might not be allowed. So there's usually, you can sort of think of it as some kind of a principal issuing a request on a resource. So I'm trying to read a file, that's OK. Someone else is trying to read a file, the policy says no. So policy is going to be determined by who is issuing the request. And the last step in this sort of sharing picture is the guard should be probably logging everything into some kind of an audit log. So this really fits with control damage and be able to recover part of the story. We want to be able to figure out what happened if something bad went wrong in the past. We want to understand why so that it doesn't happen again. The reason I draw it in a box is that you should probably keep the audit log in one of these isolation domains that's not the same as the resource box. Because if it turns out that something went wrong here and the attacker broke in somehow, it would be cool if they didn't corrupt the audit log. Otherwise, it's kind of no point for us to have logged it. So in Google's case, I believe they run a separate service that collects these audit log entries so that the service itself, even if it's compromised, cannot go back and allow the adversary to cover up their tracks. All right. Make sense, this sort of picture? We'll try to figure out what this actually concretely means in various scenarios. So what are the principles? What could you imagine, sort of, what do you worry about invoking operations here? Who are the principles in Google's design? Yeah? Yeah, so lots of things. OK, so let's yeah, sort of end users are absolutely, I think, a principle that you could worry about making an operation. Software developers, maybe. So maybe more sort of operational engineers, because software developers aren't really issuing requests to services, or they might in their role as like testing stuff. But if they're writing code, they're not really part of this picture. This picture is not about how you got the software in the first place. This picture is this thing is running, and someone is issuing an RPC to me. So maybe an employee that's whose job is to sort of operate the data center, or tech support or something like that. That's probably a principle. Other principles here, yeah. Oh yeah, absolutely. So it's really important to actually have a very fine-grained view of what a principle is, because even these end users, in some sense, it's not like I am somehow causing packets to appear. It's really I'm typing on my computer, and it's really my computer doing stuff on my behalf. It's important to keep that distinction in mind, because I might not be malicious, but maybe my computer is. And vice versa. Maybe I'm malicious, or who knows. Yeah. So it's important to really figure out what's the chain of reasoning, why you believe that a request is coming from some user. And often it's because it's actually coming from another service that's saying, oh, on behalf of this guy, please do this. Useful to think of that. Other examples? It's probably a pretty good list. You can imagine other sort of forms of services, maybe like a whole machine in Google's case. They worry about hardware security. So to them, a machine is an entity that they need to worry about, and a machine does certain things. So we'll probably have rules about what a machine can or cannot do. Questions about the principal side of the story? All right. What are the resources that we would worry about? So I guess user data, probably a big one. in Google setting. Another way you may, like, if you don't take this picture maybe too literally, maybe various sort of resources like, I don't know, bandwidth and other things that you might worry about consuming, CPU time, a little bit more abstract in that sense. But you can imagine having a similar picture in your head of like, well, we need to decide who is allowed to consume CPU, who is allowed to consume memory, et cetera. But probably user data is sort of by far the biggest entity here that we are trying to protect. All right. And hopefully it gives you some sense of what I mean by this picture. Let's try to figure out what should be happening inside of that guard box. So traditionally, in security, people talk about these guards having 3 jobs. And they often correspond to different sort of approaches to realize them. So first, you got to figure out who's issuing the request. So that's typically called authentication. So a request came in, you got to figure out what's the principal. Which end user is it? Which employee? Which other service is calling me? Which server machine is the request coming from? That's going to be important for me to have high confidence that I know who the request is coming from before I can start deciding whether to allow it or not. We'll talk about various techniques for authentication. Actually, next lecture is going to be all about how to authenticate humans, sort of end users, passwords and other techniques. We'll just sort of skim the surface in this lecture. The second step, once you know who it is, you got to authorize. So make a decision on whether this principal is allowed to do this operation or not. And that's going to involve checking the policy. And the last step is audit. So to stick this in the audit log for review or recovery, et cetera. Make sense? Questions? All right. Sometimes this is called the gold standard for the AUs that keep appearing everywhere here. Helps remind me. The unfortunate thing is auth is a tempting acronym, but it's actually not clear what that means because it's in both those guys. All right, so let's talk about these 3 parts of a guard's role in turn and try to look for examples in Google's design and figure out what are these guys doing. So let's talk about authentication first. So the probably most straightforward plan for how do you authenticate a principal, if the principal is an end user, probably some kind of a password. So you get a request, you're going to use a password to authenticate the principal. What that means is that first, you're going to get a request, and you don't actually know who the hell it's from, but as part of the request, it's going to have probably a username and a password, and then the request itself. So you'll look at the request, you'll look at that part and say, oh, well, that's the password. I'm going to log the user in. So how does the guard, what's the logical argument for why the guard should believe that the request is actually coming from the user because they got the password? Well, it's sort of slightly, a little bit convoluted, not much, but I think the line of argument in a guard is that, well, I'm going to assume that only the right user knows the password. No one else could possibly know what the user's password is. And thus, if the password came in on that request, only the user could have sent this. No one else knows this password. So I have to assume this request is coming from the user. So that line of thinking, it's sort of good to keep in mind for that's what the guard is doing, because it's sort of easy, at least in this case, to see that, well, it's a little bit suspect. Sure, lots of users have common passwords, and probably it is easy to guess a password if you wanted to. But that's sort of the, at least the line of argument for how this password-based authentication works. Make sense? So lots of people realize passwords are not great, and they use what's called two-factor authentication. So the paper talks about this to some extent as well. So the idea being that in order to log in, you need not only the password, but some other credential that's going to convince the guard that it's really you, that particular end user, that is going to be logging in. So for example, what about using the text messages, like SMS-based two-factor authentication? So you try to log into this guard, send it a request, And the guard says, well, hold on, actually, I don't know what's going on because I have your password, but maybe lots of people have your password. Let me send you a text message. You'll tell me what the code is. So is that a good plan? Better? Worse? Yeah?
It's a better plan, but there's no problem.
OK, so what's the problem you're worried about?
At least in the past, humans can get around SMS two-factor by like changing the number. Lots of human error.
Yeah, so I think, OK, so there's several issues with SMS. So let me try to first explain in a little bit more precise terms what's the line of thinking that the guard or the guard's developer is thinking. Well, they're thinking, I must have generated a random code just now that no one else knows. And then, well, the thing I did with that code is I sent it to some cell phone number. And I'm going to assume that message can only go to the right user's cell phone. And hopefully, I got the right cell phone number for them. And then when the user gets it, better stay secret. If it doesn't stay secret at any point, it's no good as an authentication token. So we better assume the user is not going to type this code into any other application. It only has to send it to the same exact guard. If the user accidentally gets confused and types that text message into some other website, now we're in trouble. So there you can already start sort of guessing as to what several weaknesses are. One is maybe you can break into the user's phone. Or maybe you can just take over their phone number. People have done that. You could imagine that the user might be confused about what application this code is for. So let me sketch out an attack for you that sort of explains why this is a tricky authentication plan. For example, if I try to log into some website, the website is going to tell me, well, yeah, OK, I need to use SMS to authenticate you. And in the background, they don't really send me a message directly. What they do is they go try to log into Google on my behalf. Well, Google sends a text message to my phone then. But I'm thinking, I wasn't trying to log into Google. I'm trying to log into this website. Let me type it in right here. Now this other website has my code. And it can, behind the scenes, go log into Google for me. This is a somewhat sophisticated attack. If this seems a little fuzzy, don't worry. We'll talk much more about this in next lecture. But there's other sort of better two-factor authentication protocols that work. So U2F is going to be a big topic and a reading assignment for next Monday. Hopefully, we'll simplify this. So that's sort of the story for authenticating humans. What about authenticating services? Employees, I guess, are humans as well, so that's fine. We'll use the same techniques. Maybe we can just force them to do two-factor auth. That's sort of, I think, at least Google's plan. What about services? How do you authenticate a service? Could we give them a password?
Maybe like an API key or IP address authentication.
Yeah, OK. So we could you can imagine IP address authentication. Lab 2, actually, for this class, does IP-level authentication because we're going to do it at a small scale. At a small scale, this may work out OK. The problem is that if you have a large network, it's a little bit hard to figure out who has what IP address. Because you have servers being plugged in and replaced all the time. You have many data centers. So an IP address might be from like 2 hops away from some other data center. You don't know what the configuration there is. So IP address authentication turns out to be a little bit error-prone to get right. So the other thing you mentioned, though, is some sort of an API or some sort of a key, cryptographic key. That turns out to be a good plan that's often pretty widely used. It's important, though, to keep in mind 2 kinds of keys you could imagine. One is basically a fancy password, basically like a long string, but it's still a string that you type in and you send with your request. This kind of a key, it's better than a password in the sense that you could probably choose a better one. But here's a really important problem with passwords that we didn't even talk about here. Here we're just assuming, well, humans pick bad passwords, et cetera. But an important problem with passwords is that you're going to send the whole thing to the other end. So the other end has your password now. If you thought you were trying to log into some website, but turns out the website is out to get you, well, you're going to give it your full password. Same for a service. Suppose we have this nice Google front-end service trying to talk to service A. If it sends a magic string to service A saying, oh, yeah, that proves I'm Google front-end, now this guy's Google front-end too. And then if he sends it somewhere else, it proliferates. No good. Or, well, it's like better than passwords. But the way to do better is to use public key cryptography. And this class is not really about crypto. we'll talk a little bit about crypto in a couple of lectures in a couple of weeks from now. But the cool thing about public key crypto from a sort of programmer's perspective is that it lets one end know your public key, and the other end knows its own secret key, private key. You can convince the other guy that it's your public key, but the other guy doesn't get your secret key and can impersonate you onwards. So it's like a good password that you get to keep. You don't get to send it fully to the other end. So that's sort of the story for authenticating services. All of these authentication plans, though, one thing that they have in common is for everything, you need to figure out how to correlate these credentials that we've been talking about on the left-hand side here with the principal name. So we'll need some kind of a directory service that is going to have to store a big table. Here's like the principal name, like maybe your Gmail username, or maybe your service name, anything else, and some kind of credential information. So maybe this is your password or something else, or like your SMS phone number, or maybe it's your public key or your API key. We're going to need this table to do authentication. And this table has to live somewhere. In a simple case, it could live just inside of the guard if you have a simple service that just has its own plan for authenticating principles. But what happens in Google's case? Where's this table coming from? How do they know what service is what and which user has which password? Yeah?
What does it say under directory?
Under directory, it has a poorly written column heading for principal name and credential info.
Thank you.
Yeah, sure. So where's this table showing up in Google's data center in their design? They don't really talk about sort of it explicitly, but what do you think is going on in Google for lining up credentials with principals? Yeah, so I think they have actually a couple of centralized services in their data center whose job is to basically maintain that directory. And it does a couple of things. I think it's used to log users in. So when you log into Gmail, this service is going to check the table and say, yep, that guy is really this username. And it's also used for services as well, I believe, that if service A wants to talk to service B, and then service B is going to need to know, oh yeah, that's really coming from service A, not someone else. They're probably going to check this table some way or another to figure out what the keys are. An alternative is you could like hard code all these keys in the guard, but then it's hard to evolve and hard to upgrade and so on. So important to have this kind of a level of indirection in the form of some kind of a directory of all your principals in the system. Makes sense? Questions? All right. So that's the story for authentication, at least in Google's design. Let's talk now about the second part, authorization. So how are we going to authorize? So again, at a high level, what's going on is that you have some set of permissions that are allowed, and it's going to be a function of the policy applied to who is calling, so the principal, and the resource. So we can think of this policy as being a function. A principal comes in. They want to do something to that resource over there. And this policy tells you, well, you can read or write or whatever operations you want. So we can imagine this is a table. You got your users or principals on this axis. And then you got your file 1, file 2 resources on this axis. And we can have this matrix of all the permissions. Maybe Alice cannot read file 1, but can read and write file 2. And Bob can read both of these files. So this is logically what's going on in the guard. Somehow this is getting specified. And it's good to keep in mind sort of two different ways you can imagine specifying this that end up being sort of materially interestingly different. One thing you could imagine is to specify rows. So you could imagine basically wrapping file 2 up and storing all the permissions related to file 2. So if you store this thing by rows, people usually call this access control lists, or ACLs. So in Google's case, they do quite a bit of this. For example, they have, of course, permissions on individual files or database records, which end users are allowed to read which objects. They have a similar story that shows up for service communication. So when you issue RPCs between different services in their architecture, there's a table like this that gets consulted. I forget what it's called, inter-service access management. Now, that was the mouthful of a term that the paper talks about, that it's like a special service, again, that runs and maintains this table by, I think, row-ish, for specifying which services are allowed to talk to which other services. And that allows the operators or administrators to limit the damage from a compromised service. So first off, they have these boxes for isolation, and then this authorization table says, well, certain services are only accessible from a small number of other places, like maybe only the front end can talk to them, and as a result, only new HTTP requests come in. Or maybe only another service can talk. So in our diagram over here, maybe the rules say, well, service B only talks to service A. You can't even reach service B from the front end. Maybe it doesn't expose any straight up HTTP requests. It only is some internal thing. So by configuring this table, the operators are able to sort of limit the damage from one of the servers being compromised and prevent an adversary from trying to break into many other places. That make sense? Questions about this? Yeah?
I'm a little unclear on how this table is related to how which services.
Yeah, OK. So here's what happens. When services try to talk to each other through this RPC protocol that Google has internally, their RPC library, I imagine, at the endpoint, like service B. Suppose that A tries to call into B. What B does is that for every incoming RPC request, you can think of this box as this box in the guard picture. The first thing that every service does with incoming RPC requests is use that, sort of have a little guard that looks at every RPC and says, well, who is calling me? They're going to authenticate it using that directory, figure out which service principal the request is coming from. Then they're going to consult some table like that to figure out if that service is even allowed to talk to them. And because they want, in Google's case, this is probably a large-scale operation, this table also gets stored at a separate machine. So very much like we were talking about there being a special service whose job is to maintain this directory, there's probably another whole service, I think this is the inter-service access management thing that the paper talks about, whose job is to maintain this table where these sort of labels are different services. So there's a separate box there that has this table, and when service B gets an incoming RPC, it goes to ask this guy, hey, I got an RPC from A, is that allowed? And then it's this inter-service access manager tells it, yep, it's OK, or no, it's not. And it might be the case that maybe it's even more fine-grained than yes or no. It might be that, well, it's allowed to do this RPC, but not this other RPC. The paper doesn't really go into that detail, but that could be a natural sort of extension you could imagine. Question?
Like, this is the actual format that these tables are in. It seems to me that this is wasteful in terms
yeah, so this is really just a logical representation of here's a function. No one really materializes this table in any form other than on blackboards. So what I meant by this sort of oval thing is that often what people do store is rows of this table. So that usually corresponds to access control lists on specific objects, so permissions. Like if you go to a file in Unix, that file has this row stored in it. If you go to a Google Doc, you can ask the question, who has access to this Google Doc? It'll say right there, here's the people you've shared it with. And that's this row. So the nice thing about storing it by rows is that you can very easily answer this question, like who has access? And that's important long term because you want to understand, have you given out too much privilege? When do you need a garbage collected, et cetera. So that's one sort of plan. I should rewind back and say, like for the service-to-service access, I don't know how they store it. Maybe it is a table kind of like this, I don't know. But for sort of file sharing kind of workloads, sort of horizontal rows are good for long-term access authorization decisions because you know what's the answer for any given file. People also store it sort of vertically, if you will. That's usually called capabilities. And the reason this is useful is that it often means that you don't need to, okay, typically the way these capabilities are implemented, it's sort of a cryptographically signed message saying, I am Bob and I have access to these files. And the reason this is useful is that It's often kind of nice in distributed systems where you don't have to go to a central service all the time to look things up in this table. So I log in as Bob. I go to the central server, and the central server looks up all these entries for me and says, oh yeah, you're Bob, and you're allowed to do this stuff. Here's a signed message for it. And now, when I go talk to all these services throughout the system, I can just present my capability and say, hey, I was told I'm allowed this. And now, they don't need to go consult this table again. I have a signed statement saying, yep, I'm there. So this is a useful technique, especially in distributed systems, because you can sort of separate out the question of looking stuff up from this table on user login from then using this capability. But it's often not a good idea for long-term storage of privileges, because you can't answer the question of who has access to the file. You might have all these outstanding capabilities. So usually what this means is that these guys are fairly short-lived. So you get a capability that's good for, I don't know, a minute, a day, fairly short terms, depending on what makes sense in a system design. Do these guys have capabilities in the Google design? In what form does this look like a capability? Yeah?
They have like an end user permission tag that services would pass.
Yes, they have this little ticket thing, which is pretty cool. Probably like the most sophisticated part of their plan from my perspective is like, wow, when I read this paper, I was very impressed. So these tickets that the paper talks about are their basically capabilities when you log in that allows services to basically say, I'm allowed currently to operate on behalf of this user. And you don't have to keep checking some table that says, oh yeah, the user really is logged in. You just assume that, yeah, the ticket is there, you're good. And these guys are also short-lived for basically the same reasons. You don't want to assume that this service stays logged in as that user forever now. Make sense? All right. So that's sort of the authorization story, if you will. As we were talking about, right, like it makes sense at the level of sort of files. The same thing shows up for services as well, to sort of service-to-service communication as well. Not always the right decision. Well, what I mean to say is that this picture doesn't always exactly line up with your worldview. I think this works out pretty well for things that are data or files. Probably works pretty well. It doesn't work well when the resource you're trying to protect is more like bandwidth or CPU. That's a little bit more funny looking. It also doesn't work super well when the policy is entangled with the data. It's like data-dependent policies are a little bit not exactly how this picture looks. So for example, if your policy was, I can view all the photos in which I'm mentioned or something like this, it's kind of a complicated view of the world according to this picture anyway. But still, good thing to keep in mind even there. All right. So let's try to talk about the granularity at which you apply this picture to your system design, if you will. So what should be a box with a guard? So you can imagine a whole data center, for example. Is that a good plan or a bad plan? Should we have that picture on the middle board be sort of at the entry to the data center? The guard is like the Google front end. They look at the request, they make all the decisions, then you're good. Good idea, bad idea? Yeah? Yeah, so basically if you guard at too big of a granularity, like a whole data center, then you have some kind of basically a trusted inside. So once you get past the guard inside the data center, there are no more guards. So it's all well and good if you got everything right inside the data center, but then if you have bugs or bad employees or who knows what, malicious services, malicious hardware, now you're in trouble because there's no more boundaries to keep things away. So this used to be actually a super popular plan in security. Firewalls are sort of the most obvious manifestation of this plan. Intrusion detection systems were, I guess, still are a popular thing that people do. Often you hear about perimeter defense. So you have your whole data center or the thing you're trying to protect. You put up a fence around it, like a firewall, and then that's what you guard. And it's like easy to deploy because you just surround all your network with a firewall. But it has this problem that you can't really defend against attackers that get inside. So this is at least some parts of this paper from Google are really trying to articulate. This is probably one of the better papers describing how do you really do something other than firewalls. And the splitting up per service is a much more sophisticated and, I think for them, effective plan. So you could imagine each service. That's roughly what Google is doing with their design here. Every service being one of these boxes. And sort of the reason, or like I want to articulate one reason why this is cool is what's in the security community often called the principle of least privilege. So the way you should think about building a secure system from an architectural perspective is that you should break it up into small boxes and give each box the least privileges that it needs. Because if it has too much privilege, then, well, if someone breaks in, they can abuse that privilege and cause some damage. But if each box has the least amount of privilege necessary, then the damage is sort of minimized to the minimum damage necessary if that box was broken into. So this principle of least privilege is an important thing to keep in mind as a guideline for how to orchestrate all your components in a system. And having more fine-grained components allows you to make this principle of least privilege more effective because you have smaller boxes and you can give each one maybe fewer privileges than if you had a big box. Data center has sort of all the privileges, and then the further down you go, you could imagine it being more effective to reduce privilege here. To some degree, in their paper, they actually do something even fancier than per service. They, to some extent, do some per user isolation, so this ticket thing that they do. You can almost think of each user now being a little domain of its own that's being protected. It's not entirely in the same shape that I've been drawing on a board because they don't actually have per user boxes for the most part. So they don't actually run a separate VM for every Gmail user. They could, in principle, do that. And it'll probably be stronger isolation to some degree because then each user's Gmail box would be independent of whether someone else broke into their Gmail box. But not super practical because these boxes are, to some degree, costly. So one question that actually we got from a bunch of student questions was what's sort of the performance overhead of this whole plan? So many students were reading this paper and saying, wow, that's like 14 pages of extra stuff, all for security. Must be slow. So what is the overhead, actually, of their plan? So like looking at their overall picture, where is this security plan impinging on performance or on the critical path? Are there any overheads? Yeah. Yeah, so having to talk to, so like RPCs are definitely one source of overhead. If you didn't have to do an RPC before, now you're doing an RPC, maybe that's more costly than otherwise would have been. Absolutely, yeah? Yeah, okay, so RPC is one. Encryption is another potentially source of overhead. I guess I should write it there, but yeah, so encryption of two forms. Encryption for RPCs themselves going over the network, but they also do data encryption on disk as well. So that also, you can imagine some sort of overhead there. In the paper, they worry a bit about actually encryption overhead. They talk about they are not encrypting all traffic within a data center, I believe. So they encrypt all the traffic between data centers, but I think at the paper, at least this was 2017, they said, well, not every RPC within a data center is encrypted. Sometimes those are plain text. So that's indeed, yeah, one source of overhead is encrypting RPCs, encrypting data on disk. Other things. Yeah? Yeah, so they make this whole big deal about data deletion. It is certainly a thing that happens, like actually happens on some computer, but it's not on the critical path. It's not like your performance suffers of using Gmail, or probably doesn't, I imagine. At least if your common workflow is not deleting your data, then probably it's okay, yeah. Yeah?
I think if we're relying on GFE being a centralized service, it could become a performance bottleneck.
Yeah, okay, so yeah, to the extent that you cooked things up, and like maybe GFE, that one they actually say is highly distributed actually, but other components, like we were talking, we need a service that's got that directory. We need a service that's got that access control matrix. If those guys are on a single machine, well, now all of a sudden we gotta all talk to this single machine. So yeah, so another possible source of overheads is centralized some sort of a security services. Yeah, it could be a performance bottleneck for sure. Other things. Yeah?
Updating these databases across the distributed machines.
Updating like the directories and the access controls, you mean?
Yeah, like how do you update them all at the same time?
Yeah, so I guess, yeah, so these centralized security services could be just like maintaining them is expensive, querying them is expensive, yeah, potentially. So I think this is a pretty good list. This is roughly what I was thinking as well in terms of like what actually happens in terms of overheads. So the cool thing is, my sense from reading this paper is that this is indeed a fairly short list of things that go wrong, or sorry, I don't mean to say go wrong. These are like the only things that actually happen on the critical path of you running operations against Google's applications. And the cool thing is I think they have to do all this stuff anyway. So RPCs, they have to do RPCs anyway because they're running across many machines. And because of their scale, they have to do RPCs between servers, so they're not seeing a huge increased overhead from RPCs because of using them for security. In many ways, this paper is not a purely security reason for why this whole thing is architected. This paper describes what Google is doing anyway, but there's many other reasons why they architected their data centers in this way, for availability, for management, for performance, et cetera. So it turns out I think these RPCs may be an overhead source if you are doing it all on one machine. If you're distributed, you got to live with that anyway. Encryption ends up being cheaper and cheaper and cheaper over time. So I think at the time they were writing this paper, 2017, this was a little bit of a problem for them. I think these days, I believe there are all encrypted traffic everywhere, and this stuff is just getting super cheap. You have accelerators in your CPUs for doing crypto, so probably first level approximation of encryption is just free, you should think of it. Should worry about performance overheads from that. And they figured out a bunch of good ideas for how to distribute these security services. So even though they're logically centralized, there's one entity that can give you an answer for what's in that directory, for example. There's a nice paper that they wrote recently about how they actually run this service logically across many, many VMs. They're all consistent, and they're able to give super fast answers for queries about who is able to access what service or what file. So as it turns out, despite sort of having a very sophisticated sounding security plan, I think the overheads are actually not anything too exciting. I think more or less it's what it would have been anyway. And the reason I sort of started talking about it is that we were talking about the granularity of isolation. I think one reason why they're not doing something crazy like per user isolation is they need performance. Service level isolation and guards seem sensible because you have to do it anyway. Per user would be too much overhead and would be more secure, but probably this is not a performance price they're willing to pay. Make sense? Question back there.
Consider encryption as a subset of granularity in some sense?
Can you consider encryption as a subset of granularity? I mean, I guess you could imagine worrying about encryption, like trusting your network at some levels and not trusting it elsewhere. So if you trust your data center network, this is what they used to do. They didn't used to encrypt within a data center. But I think what they're seeing more and more is they have much more mixed deployments. So what I mean by this is they make a big deal in the paper about being a multi-tenant data center. So they're actually mixing workloads from Google internal stuff like Gmail, their own data analysis, their cloud customers. It's all running on the same set of servers and the same switches. So it seems like a good idea to not actually trust any component. So their sort of overarching trend seems to be pushing the security boundary closer and closer to the service itself and not trusting as much infrastructure as possible. So to the extent that they can avoid trusting the network, even within a data center, it's great. They have this interesting part in the paper where they talk about, okay, well, like, what do we do if we're not the owner of the data center? Sometimes they have Google servers in a data center they don't fully control. So maybe they have to use someone else's network all of a sudden. Or maybe it's possible that someone else will plug something into their network. So probably a good idea to not worry about that by just encrypt authenticate everywhere. Yeah. Make sense? Questions? All right. So let's talk now a little bit about their use of trusted hardware and what's going on there. It's kind of an interesting story. So I guess we talked about authentication. authorization. Audit is sort of important, but there's not a whole lot to say about it. You should just log the decision. Like timestamp, principal, access this resource because this policy said so. And important to put it in a box. But that's roughly sort of what's going on. Google, at least in this paper, talks about that being important for them to worry about insider attacks, where some of their employees might be either compromised by their password might be compromised, or they might be themselves trying to break into something. So they have a whole team inside, apparently, whose job is to sort of look at these audit logs and try to analyze them for suspicious activity. So that's, I think, the main thing the paper talks about, auditing, if that makes sense. But otherwise, unfortunately, I have nothing too interesting, too exciting to say about auditing. Sort of all heuristics in terms of how you understand whether something is wrong or not. So let's talk about their trust or mistrust of hardware. So in the paper, they make this big deal about some security chip that they embed in their server computers. They don't really explain this super well. So I'll try to guess, if you will, what they must be thinking about, and then we can argue about what it solves or doesn't solve. So I think what's going on is that they're imagining they bought a server. So here's a server. They bought this guy. They plugged it into their machine room rack, and they connected it to a switch. So here's their network. And the question they're asking themselves is, should we trust this machine? Should we now start running some workloads on it? So the kinds of questions is, well, should we store a copy of some user's Gmail data on this server? Should we run the calendar service here? Should we run the GFE service on this machine? And the attacks I think they worry about are several. They don't super clearly articulate them, but I think they're roughly worried that this server might not faithfully run what is given to it. So I think the stuff they worry about is the server probably has a BIOS, which is the boot code that starts when you push the power button on the server machine. It starts running the BIOS code, whose job is then to load the operating system from disk. So there's probably some operating system over here with a kernel and all this stuff. The BIOS loads the operating system, then starts running the OS. So that's the software running on this machine. And there's some kind of a central data center manager whose job is to sort of keep track of all the registered servers in that data center and then send them stuff to do. So some request comes into the data center manager saying, I just got plugged in. Let's go. And they're trying to figure out, should we sometimes say no? So what are the attacks they're worried about? Why should you ever say no? You got the server. Let's use it. Yeah?
Maybe the BIOS or other software has been tampered with.
Yeah, so I think one thing they're certainly hinting at is that for whatever reason, this BIOS might not be right. And maybe it has a bug in it. Maybe someone put a backdoored BIOS in here. Maybe the operating system is the wrong operating system on disk. It's a little bit fuzzy what they are imagining actually happened along the way. So we could try to speculate as to how did they end up with a bad BIOS. So I imagine maybe what they're thinking is, well, an easy thing you could imagine is, at one point in time, this server was broken into. Well, that's kind of unfortunate. But when the attacker broke into the server, they changed the BIOS. Now that's kind of damaging because you might have reinstalled the OS, but the compromised BIOS is still there and it's got a backdoor. And when it loads the OS, maybe it puts an extra account in the OS password file or something like this. That would be sophisticated, but at least within imagination. Like people have done this on Apple laptops, for example. If I remember correctly, there was a cute attack on iOS Apple devices where some malware inserted itself into, I think, either the keyboard or the battery controller. So even though you reinstalled macOS, the malware would still be there in your battery controller's microcontroller and might try to exploit some bug in the OS again later. So this is the sort of family of, I think, attacks they're worried about with respect to the BIOS. Probably another attack they worry about is whether maybe their hardware manufacturer shipped them the wrong BIOS. Maybe by accident, they shipped an old version of the BIOS. They ordered a bunch of servers. The manufacturer didn't install the most recent BIOS on all the machines, and the older BIOSes have bugs in them. I think that's another source of worry for these guys. Yeah?
Detail what the BIOS is and what it does?
Yeah, so what happens is on any machine, really, what happens is you have a CPU in there somewhere. It powers up. It needs to run some instruction. Where is this going to come from? The CPU doesn't really know how to talk to a disk. Disk is kind of a complicated thing. It takes forever to read stuff from disk, etc. So what happens is the CPU is probably attached to some kind of a memory bus on which sits a little memory chip that probably like a flash chip. Picture is more sophisticated than that, but roughly, the CPU immediately starts running instructions from this flash chip. And this flash chip is fast, can give the instructions right away. That's not a whole lot of code there, and probably it's not even code that is part of Windows or Linux. That's actually comes from Supermicro or whoever sold, or Dell, or whoever sold you this computer. They write a little bit of code in here. And the goal of this code is when the CPU powers up and starts running this code, it is going to then slowly initialize the PCI controller, the disk controller. It's going to go read disk, figure out what operating system you have installed, read the kernel from disk into memory, and then start running the kernel. So it's basically like all the stuff. You power up this thing, it's got a fancy logo on your screen. It says press F12 for this, F1 for that. That's all BIOS code. And when it starts running Windows, it's finished basically running the BIOS code. Now the operating system is running. So it's an important part of the machine because it actually has full control of your hardware even before the OS does anything. It's not even loaded. So sort of, you can think of it in two ways in terms of security. One thing is that the attack surface is maybe not that big because when the computer is booting up, it's not like the attacker is pushing buttons on your keyboard. So the BIOS is running in a nice isolated environment, probably doesn't get exposed to too many attacks. But super privileged because before it runs the OS can't guard against it at all. So that's sort of the context of what the BIOS is doing in a typical machine architecture. Make sense? Other questions about this picture? OK. So what are these guys trying to do about it? What's their plan for how to deal with this compromised BIOS or a bad OS on a server? So as far as I can tell, what they do is Google tells their server manufacturers to stick a little security chip into every motherboard. That's sort of wired up to the server in some way or another. And the job of the security chip is to maybe even run before the BIOS starts running on the CPU. That part is not really super well spelled out. But in some way or another, I think what's going on is the security chip is reading in the BIOS and computing a hash of it to figure out, well, here's the BIOS we're running. And then probably reads and somehow computes a hash of the kernel that gets loaded up and maybe some other parts of the OS. And then the security chip keeps that in memory. So it knows how the computer booted up. So by the time the server starts talking to the data center manager controller, saying, oh, I'm a server, let's start using me to store data and run jobs, the security chip is already recorded. Here's the BIOS we ran, here's the kernel we ran. And the security chip is going to sort of attach a little certificate, I think, to this request. So the data center manager is going to get basically two pieces of data. One from the OS kernel running on that machine saying, I booted up, I'm a server, let's start using this, as well, plus a certificate from the security chip saying, yep, I just watched this thing boot up. It had this BIOS, this kernel. And now the data center manager can use that to make a decision as to whether this is a good server or not. So the security chip probably has some sort of, I don't know, a serial number or some sort of a key inside of it. And I imagine the data center manager has a table of basically all the security chips Google ever manufactured. So probably here's like, a chip, serial number and key. Here's a table of all the things they think are valid. If it's a valid one, they'll trust it. If there's no security chip, they will not trust this machine. If this is a serial number or key they don't know about anything, they will ignore it as well. And then on top of this, I imagine they'll also check the hash of the BIOS and the hash of the OS kernel that comes from the security chip to make sure it's an up-to-date BIOS and an up-to-date kernel. And if it's not, they'll probably send a command back saying, well, you're out of date. Update before I'll do anything with you. So I think that's roughly what they are describing in their hardware security plan there. What kinds of attacks does this actually help with or not? Yeah? So code injection of some sort. OK, so suppose a code injection attack. This thing boots up. It's running Linux. It's got VMs running on it. All of a sudden, someone exploits a bug in the Linux kernel. Is this going to guard against that? Probably not, because I think what this guy is tracking is just what booted up. By the time it's booted up, it's already and registered. It's already running Linux, all these VMs. The security chip is not really going to come into play while this thing is sort of up and running. It might come into play again when the machine reboots. So if this code injection attack that you mentioned turns into the adversary modifying the kernel on disk so that there's this persistent backdoor here, or if the attacker modifies the BIOS in the flash chip, reprograms it, then the next time the server reboots, then it'll look like a bad BIOS, and then it'll probably set off some flag in the data center controller here. But it's not super, I think, not effective at all at just like guarding against like a garden variety buffer overflow that just happened. It's really sort of, I think, stopping the subsequent effects. Like even if you exploit a buffer overflow in this kernel, after the OS gets reinstalled, we should be good to go. And this will make sure that you didn't stick anything bad in the BIOS to keep yourself there as an attacker. All right, so what other attacks could you imagine, and whether this actually works or not for this? Yeah?
I mean, I don't. And could the BIOS, I mean, since the BIOS has sort of like access to everything, could it insert something that then watches the bus, and then when the security trip, or DC manager tries to talk to the security chip, it watches the bus and then like lies about their response?
Yeah, so you're trying to figure out like, well, how's this actually going to work? Like, is the CPU running the BIOS or not? And if the CPU is running the BIOS first, can we just like, reboot the security chip or something? How is this happening? It's like too bad the paper doesn't really say. You could imagine doing this wrong. There's been various systems that do this wrong. For example, there was a popular chip called the TPM that mostly got this, well, wrong in some ways, that had the various attacks you're describing. Other chips work differently. So I don't know. So I think, indeed, if you're a super sophisticated attacker and maybe you control the BIOS, or actually if you control the motherboard, I'm sure you could miswire this chip. So I think this is not really a defense against, let's say, the motherboard manufacturer. If the motherboard manufacturer is really malicious, they, I'm sure, will take Google's chip and wire it up to like some special pins that always give it the right BIOS, and that's it. So I think those kinds of attacks are probably not going to be super effective against this. But at the same time, they're probably not, I think in the context of the BIOS, I don't think Google is thinking their supplier like Dell or whoever in Taiwan or China is trying to screw them over by like shipping them really compromised machines, or Intel sending them bad chips. I think they're worried that these guys are just incompetent. They're just like, they're going to pull out some old BIOS chip from a box and stick it in the server. And they forgot to update it. So I think it's a little bit hard to delineate what exactly attacks are in or out of scope for this, but I think these guys are worrying about, at least the BIOS level, sort of not super sophisticated attacks. Yeah?
But I mean, this whole thing doesn't really prevent people from like manipulating the software on the network adapter or like the SSD, for example, the SSDs which are in solution.
Yes, that's an interesting question. Like, there's lots of firmware elsewhere in the system. I think that certainly Google's intention is to somehow deal with all that firmware. And I think they're slowly making some progress from what I hear from talking to these guys. But it's kind of pulling teeth because the manufacturers are not super excited about this. Other companies aren't really asking for it yet. So I think they'd like to do this, but it's hard to do this in the context of the hardware that's available for the most part. But you're right, yeah, there's lots of devices in a computer that might be malicious. OK, so the attacks that this does actually work well with is probably something where someone plugs an extra server into the network. Like a janitor or someone in a data center walks up, plugs a Raspberry Pi in the network. This will work pretty well. You just can't get a Raspberry Pi on the network to become a Google server. It doesn't have one of these chips. So it's somewhat effective against this attack. And otherwise, actually, without the security chip, you might actually have a hard time figuring out whether this Raspberry Pi is really a legitimate Google server or not, because there isn't really any state to begin with on that cleanly installed machine. So it is sort of interesting for some class of attacks anyway, but probably not super determined attackers at the manufacturer. Yeah, question back there. How secure are these security chips? Interesting question. Yeah. So maybe the one positive thing I'll say is that, well, it's hard to tell. The Google hasn't published a whole lot about them. There's a recent effort by Google on a project called OpenTitan. You can Google this. It's a pretty cool project. They're basically open sourcing fairly low-level hardware details. Here's the layout of this chip and how to manufacture it. And I think they're trying to get credibility and sort of momentum in the community to standardize on some sort of a security chip, what it does, what it might do, et cetera. So there's some effort there. The thing that's actually used in Google servers today, I don't think is super well documented. And I imagine these guys are trying to do a good job at it. But it's hard to tell exactly what's going on. I think one thing going for it is that it's a small chip in terms of the amount of software running there. So less software means fewer bugs. And I imagine it has very few ways to poke it. So there's very few ways that a hacker could try to abuse it or break in. So I imagine it's much better than the rest of the server here, but yeah. How are the keys in these chips managed? Yeah, that's a great question, because somewhere, like who's making this chip and who's plugging it into the server? They don't really say. I think what must be going on is that they contract with some hardware manufacturer to print a whole bunch of these chips with known serial numbers and known keys, and they register it in this database first. And then when they order, I don't know, 10,000 servers from Dell, they send Dell a bag with 10,000 chips and say, well, stick one of them in one each server, or something like this. But I'm not sure. Sorry? I imagine there's probably some kind of a root key in the security chip. That's like the private key of that server's chip. And it's used for signing messages, but I don't know, maybe it evolves over time. You could imagine some scheme for doing that, but that's like not really specified. That's one nice thing about this OpenTitan thing. At least there, it's like you can go to GitHub/OpenTitan, and it's all there. But I think it's not nearly as sophisticated or fully fledged as the thing they're actually deploying in their servers today, I believe. So starting to get there. Other questions? So that's part of the story. Admittedly, it's like a bit of a, I wish the paper said more about this, because it sounds something really cool that other servers aren't doing, but the details matter a lot and aren't really as well spelled out here. All right, so talked a little bit about this hardware. Let's talk a bit about availability as well. Another problem that we talked about as being important. So availability problems roughly translate into denial of service attacks. So denial of service attacks mean you got some service over here, and it is getting way too many requests. And the way to think of denial of service attacks is that you have limited resources when you're running your service. There are some kind of resources, conflict of terminology. This is not the same kind of resources as here. Here we're talking about something like user data that you want to guard. And here we're talking about resources like bandwidth, CPU, memory, those kinds of resources that you might exhaust. And then if you have too many requests that exhaust your resources, CPU, memory, or bandwidth, then all of a sudden your site stops working for many users because it's run out of bandwidth or memory or CPU time. That's a particularly difficult kind of an attack to deal with because there's not a whole lot to do to just fundamentally prevent denial of service attacks. And it has to do with the fact that the internet is this open network. Anyone is allowed to talk to most services. And these requests, when they first come to a service, they're not really authenticated. It's just some packet from some IP address. And you probably can't do too good of a job at filtering by IP address. So hopefully it makes sense as a problem statement. So denial of service attacks exhaust some resource. There's fairly few techniques that people have figured out for DOS mitigation. Good to know. They're not perfect, but roughly, you need lots of resources. There's no getting around that. If you want to deal with DOS attacks, you have to have lots of resources to basically throw at this problem so that it's OK if an attacker sends lots of requests your way. And the reason it works particularly well for Google's case is that, well, first of all, they do have lots of resources. And second, because they're hosting lots of different applications, lots of cloud customers, not all of these resources are needed for all the customers at once. So one guy is getting DOS now, another guy will get DOS tomorrow. So they get to share this pool of resources to deal with DOS attacks. So aggregation turns out to be a particularly useful trick here. And then basically the deal is you want to authenticate requests as soon as possible. Authenticate. And the earlier that you can authenticate the request, the reason it's important to authenticate requests is that once you know who the request is coming from, then you can say, well, this is a real customer. I know this guy. He's paying me money. Versus this is a bad guy or someone I've never seen before. If I'm overloaded, I'll drop a request from someone I haven't never heard from before. So once you authenticate requests, you're in a much better position to then decide by user or by principal. So then you can apply all kinds of rules saying this is a registered user, this is not a registered user. And up until the point you've authenticated a request, you basically want to be very careful and really minimize the resources used before you've authenticated. Because before you've authenticated a request, you have no idea if this is an attack or not. And if you spend a lot of resources on a request before it's been decided who it's coming from, you're basically throwing it all away because it could be a bad guy and then you've wasted all these resources. So one corollary of this is that it's like a little bit tricky to write this code to carefully handle requests without using a lot of memory, CPU time, etc. So factoring it out into some common service like the GFE in Google's case is a pretty good idea because tricky stuff to write, to be very resource conscious. The GFE does this well for Google, I imagine. And then from that point on, you've authenticated the request, figured out who it's coming from maybe, and then the later services can decide whether they care about these requests or not. So I have a super high-level plan for what people do about DOS attacks, and it maps pretty well into what Google is doing with this GFE thing, which is sort of their front-end load balancer for these attacks. Question? Yeah.
This is a bit vague, but how large are the distributed denial of service attacks that Google can handle? They mentioned like filtering traffic.
Yeah. So I think the easy things to measure, so you're asking about how big these attacks are. The things that are easy to measure are things that go after bandwidth. So those are basically just like straight up packets that are not actually even interesting requests. I think last I remember reading numbers, upwards of like close to a terabit per second. That's a lot of bandwidth. Google has that bandwidth, but it's like noticeable for sure. So there was a journalist, Brian Krebs, who runs a popular blog, and he has many cyber criminals that are not excited about him. And they mounted an attack against his website that was hosted on Akamai at the time. And actually, Akamai, I think, was hosting this guy's site for free or something at the time. And Akamai was basically having quite a bit of trouble, if I understand correctly, handling that denial of service attack, even though that's sort of their business case. So they actually asked the guy to move to Google, his blog. But anyway, I think there's some technical difficulty with Akamai. I'm sure they fixed it by now. But it is tricky to get this stuff right. You have to have a lot of resources. And CPU and memory are like even trickier to deal with because anyway. All right, so hopefully that was interesting. We'll talk about user authentication on Monday next week. See you guys then.